All right, let's jump into it. Welcome everyone, my name is Maciej.
And my name is Jan. And together, today, we would like to talk to you about hardware TCP offloading. And we have based our webinar on our internal project that was focused on MQTT protocol. So let's see what the plan for today is. First of all, we would like to present you a quick introduction where we will recap what is MQTT protocol and what do we actually mean by offloading it. Then we will go and delve deeper into the challenges that we have faced in our project, the solutions we have tried to actually solve the issue at hand, and finally we'll wrap up with a Q&A session. So if you have any questions, please leave them for later. So to start off, let's consider MQTT. MQTT stands for Message Queue Telemetry Transport, and it's a protocol for IoT where we have three kinds of entities present on the screen. And MQTT uses TCP as its own transport, which will become important later. So what is the workflow that MQTT uses? First of all, the subscriber subscribes to some kind of topic, registers within the broker on this topic. And then when the publisher sends the message with this mentioned topic, the broker decides which subscribers match the topic and sends them the message. So the workflow is really simple. And what do we mean by offloading this workflow? As with any offloading project, we have two goals. We want to reduce latency on some kind of critical path. In our case, it's the distribution time. So the time from the sending the message by the publisher to receiving it by all the subscribers. And the second goal is that we want to reduce load on the host CPU. So we took a look at the MQTT broker, at the functions that it provides, and decided that there are two most common and most heavy operations, meaning the packet distribution and the matching of subscribers to the topic. So we want to move those two functions from the broker to our protocol offload, and in this way accelerate this protocol.
However, we didn't want to move all the other fun stuff related to broker that the broker does, like subscription management, the web servers, telemetry, all the things around the actual processing of the published packets. Because in that way, the easiest way would be to just move the broker application from one place to the other and be done with it.
Yeah.
But that would be too easy, right?
That would be too easy, but we did actually consider it for a moment, since it would actually provide us the benefits we want, at least in theory. So, with this concept, how the workflow in MQTT will look like with after introducing the offload. So, we have new entity, we called it protocol offload, and it will be realized on some kind of smart NIC. As previously, we are starting with registering the subscriber within the broker. And this type of function needs to be first realized in the broker. So the protocol offload needs to pass these messages to the broker, and then it will notify our protocol offload on this new subscription. In this way, the broker and protocol offload have the same state of the subscription topic map.
So as we've said, we are not managing the subscriptions in the protocol offload per se. We're still bypassing those to the broker.
Yeah. And the next function from the MQTT is publishing messages. And this function will actually be handled fully in our protocol offload. So this is where the offloading magic will happen. Yeah. Our protocol offload will receive the message from publisher and then produce all the necessary messages for subscribers depending on the previous registrations. So we have this very generic and very simple concept. Was the implementation and underneath really that simple?
Well, it seems to be that there is more than meets the eye. It would be just simple moving back and forth the packets from one place to the other, right? Or just capture them at the broker. On the protocol offload instead of the broker, and then just send them from one client, capture them, and then send them to the others. But it doesn't work like that, right? Of course, the offload, as we've mentioned, is going to sometimes receive and sometimes transmit the packets on behalf of the broker. So it's not just simple packet filtering. It's not data manipulation. That some functions that the SmartNICs normally regularly realize. So in other words, the offload is going to generate and terminate the packet reception on behalf of the broker. So it means that it's going to be an active endpoint. It's going to be independent from the broker. For the same thing, broker is also an active endpoint, so it's going to generate and terminate its own reception of its own packet. But it has the host operating system network stack to handle all the lower layers that are beneath the MQTT. So since the offload is also an active endpoint, it's going to require the same network layer guarantees and features that the broker is using. And unless those features, those mechanisms, are provided to the offload by some external mechanism, let's say, an engine, FPGA mechanism, so on and so forth, the offload has to implement and handle all of these layers on its own. And so let's go through quickly through the layers that it's going to have to handle in case of MQTT. Starting off with the lowest one, the Ethernet. The protocol offload is going to, obviously, while generating packets, will have to fill in the destination MAC address, but it has to know which MAC address fits which client, so it has to know that mapping. So it might get it statically from broker, let's say, or learn it, or upfront from some kind of communication, or learn it dynamically using like mechanisms related to a learning switch, let's say. Also, on the layer 2, the protocol offload might have one or more physical ports. If there is more ports, and some of the clients are spread across those ports, so we have a more complex layer 2 network, so the infrastructure is a bit more complex, the protocol offload will have to be more complex as well.
So in the most extreme case, we would have to basically implement a L2 switch in our offload.
Yeah, exactly. But instead, it would also have to be learning. There has to be something interesting. Same goes for IP. The network, the infrastructure can be more or less complex. All of those clients might stay in a local network. It might also be some kind of remote network. The protocol offload also might be handling one or more network interfaces, IP interfaces, so use different addresses. It has to know the mapping of IP to destination MAC. Maybe there's going to be a necessity to support ARP protocol, but if the protocol offload is handling remote networks, there might be also a necessity to interface with gateways. And going up with TCP, that's where the fun part begins, because the Ethernet and IP are not necessarily connection-based, right? They're just send packets and just believe that it reached the destination. With TCP, you have point-to-point connectivity, and in case of broker to client, it's very simple. So it is a very simple case. We have a server and a client. They're connecting. They're in sync. There are mechanisms that are used by both of them to just keep themselves in synchronization, like sequence and ACK numbers. Introducing a protocol offload. Let's say not in between, let's say, but on the same TCP connection, unless the protocol offload is establishing its own connectivity. The protocol offload, since it's sending the packets on behalf of the broker, is going to act as if it was one of the sides of the connection.
Yeah,
and
that's the first layer we encounter, some kind of state, yeah?
Yeah, we're effectively having a stateful connectivity here. So as we said, initial state is that the broker and client are in sync, right? But the moment we introduce the protocol offload and the moment we send at least one packet using the sequence and ACK numbers that the broker would normally use for sending the packet, it's going to send it. The client is going to receive it. However, if the broker tried to do the same thing using its own sequence ACK numbers that the protocol offload already used, it's going to cause the client to drop the packets that are coming from the broker to the client, which in effect might cause the TCP connection to be finished by the broker, which we don't want. But that's just the tip of the iceberg, right?
Yeah, surely it is. There are many other problems, features expected from TCP, and our offload would need to guarantee those. Due to time limitations, we wanted to showcase you one of the issues, but other we have mentioned in our ebook associated with this webinar, and the link to this ebook will be presented at the end of the presentation. For now, let's consider how we could deal with those guarantees. And we have some existing hardware offloads available.
Yeah, the existing ones to provide the guarantees to the offload.
Yeah. Usually, those guarantees are provided by the by the operating system network stack. So the network stack uses those offloads, but in theory, we could use them as building blocks and implement the network stack by ourselves.
Just the network stack are doing, right? They're just accelerating whatever they're doing with hardware things.
Yeah. And a few examples that we wanted to mention are receive offloads and, for example, large receive offload or generic receive offloads, and transmission offloads, like TCP segmentation offloads. But none of those really guarantee the synchronization of the state. They rather monitor the state.
Well, they could help a bit in just creating the larger TCP packet or payload in case it was fragmented, like maybe with IP also. With transmit the same way, it might segment the packet, but it's not dealing necessarily with synchronizing both broker and the client, right?
Yeah.
Sorry, broker and the protocol offload to transmit the packets correctly, right?
And we have another class of devices or hardware offloads called TCP offload engines. And in this case, the whole network stack, TCP IP network stack, is moved outside of the operating system. So we have usually a mixture of software and hardware implementation that provides all those guarantees that we expect from a network stack. But
it doesn't also it doesn't tackle the thing that we've mentioned, the huge elephant that you're going to talk in a moment. But the protocol offload, TCP offload engines are not yet adapted for one reason or more reasons.
There is no interface in Linux basically for them. So you still would need to deal with this offload engine outside of the operating system, which can be tricky. And in our case, there is a difference that is present, and the consequence of which is that we want to actually provide our own implementation. In our case, we have two entities that are present on single TCP connection and actually act as a single endpoint. We have both broker and the protocol offload, and part of the TCP stream sent from the subscriber needs to be passed to the broker, part to the protocol offload. So, and the result is that this architecture is not really supported by the hardware offloads we have previously mentioned. We still need to develop something in our own way.
Yeah, but it's also not related necessarily to MQTT, right?
Yeah.
It's basically whatever, if you have any TCP-based protocol, it has to selectively handle a portion of the protocol. It's going to face the same issue, right?
Yeah. From the last, I think, 5 slides, we have not mentioned MQTT in any way.
Yeah, exactly.
We are basically talking about TCP.
Mm-hmm.
So with this overview, Maciej, could you tell us more about how we could approach the problem?
Yeah, so we've actually tried to implement a couple of proof of concepts ourselves just to try out whether we can get any better than the reference solution, so basically a direct connection between the broker and the client. And the first thing we tried is to monitor the existing TCP connections. And how it effectively worked in our case is that what we thought about was to introduce the offload in between the broker and the client, as if for the subscribe to the packets that are going from subscriber to the broker, we're passing it through the protocol offload.
Yeah.
there is an ongoing connectivity between the broker and the client. We're putting in between. The protocol offload is going to sniff the sequence and acknowledgement numbers between the broker and the client. Here we have one side only, but it's going to be sequence ACK on both sides. And we are also providing the mechanism, aside from monitoring. We're using a translation mechanism for the packets that are going between the broker and the client, so that even though the broker and the client are out of sync, which would happen, as we've explained, after the protocol offload would independently send at least one packet on behalf of the broker or the client, depending on in our case, for MQTT, that will be the broker. We are dividing that one synchronization domain. Even though the broker or client are not in sync, the translation will, using the translation mechanism, is going to keep those convinced that the packet belongs to the connection, even though it doesn't seem to be globally.
So basically the idea is that we still have this single TCP connection that was at the start. And sometimes we are messing with it to keep the connection in sync, despite the broker and client having different views for it.
Yeah, in other words, it's a man-in-the-middle attack on a TCP connection, effectively. Implementation-wise, I don't know if you've mentioned, but we are using NVIDIA BlueField-2 DPU. And we were realizing the protocol offload as a software. In FPGA, that would be a huge lift for a small proof of concept that we were aiming for. And the main goal of this activity was just basically to provide a very minimal viable product just to see if we can get any better, right? So we've implemented the sequence ACK translation. In here, we have abstracted internally the other side of connection. So we're saying for the broker, where we have sequence number for here, we have a client abstraction for the broker. And here we have broker abstraction for the client. This is for sequence tracking, so basically sequence ACK number tracking on both sides. So we are clearly separating the synchronization domains here, and we are translating in between so that the packets are meant by the client or by the broker that they belong to the connectivity. We have MQTT processing of the packets that we've stripped from the headers, and also we are relying on the gRPC notifications from the broker that the new subscription happened. As for TCP aspects, so we've mentioned a sequence ACK desynchronization in detail. We've said there are plenty of more problems that you might face. However, we are just solving one of it. Well, simultaneous transmit, yes, of course, because all the packets are going through a single point. That's why. However, we are not touching anything else. However, we've managed to run at least a very minimal scenario with success. And see what we're going to show right now.
We have basically implemented minimal features to keep the connection alive for time to run tests.
Yeah, exactly. If we didn't do that, well, effectively we tried to do that without it, but obviously it failed, right?
Yeah.
But what happened is that we've managed to run at least a very minimal scenario, and we've started measuring MQTT publish distribution latency. So as you mentioned, the time between the publish transmit and arrival of the disseminated packet from the broker. On the subscriber side, we had initially one publisher, one subscriber, and 2 packets per second sent by the publisher. And we were measuring our test scenario with the offload and with the reference, so direct broker-client connectivity. And in this case, we are seeing somewhat 30–40% decrease in the distribution latency, which is very good. However, we've also tried a bit more. We've tried to add a bit more publisher subscribers. The improvement is still noticeable. It's not better, but it's still very good. However, you might say that the test configuration is somewhat vestigial, even, right? It's very small. It's not. I wouldn't say it's a huge load. However, the introduction of additional publishers caused Nagel's algorithm to kick in. So basically, the offload that we've implemented was not ready for the packets that were the MQTT packets that are jumbled in a single TCP payload and cut in the middle, for example. So it wasn't ready for that. And also, we've seen the retransmission happening, which completely wreaked havoc on the simple sequence ACK number tracking. However, as you see, we've managed to achieve some improvement. So that said that to us that further tempering is justified. So let's play around a bit more. And also, we've noticed that the connection peer abstraction idea used in sequence ACK translation, so basically abstracting the client side for the broker and the broker side for the client, is an idea very close to a socket, aside from the protocol offload actually establishing the TCP connectivity to either broker or the client. But we are getting close to implementing an actual TCP IP stack. And also we've seen that the problem, the problem is that we haven't solved any of the problems that we had with TCP aside from sequence ACK desynchronization. So we've kind of thought that let's go maybe with a TCP network stack, let's try to integrate it. And so
basically more complex features of TCP hit us in the face.
Blew it in the face when we tried to run at least something more significant than very minimal thing. So we went with integrating the network stack, right? We've decided to ditch the TCP monitoring functionality whatsoever altogether, right? We've decided to embed a network stack and then run MQTT processing on top of it. In our case, we've decided that the client should connect to the protocol offload now. And for each connection to the protocol offload, the offload would just connect to the broker, establish a second connectivity.
Yeah, so we are replacing the single TCP connection by a connection pair. One from the client to protocol offload and the second
we had single connection to the two synchronization domains. Now we just run the very TCP correct way of two synchronization domains.
Yeah.
And implementation-wise, obviously, for the network stack, we've decided to go with lightweight IP. There are multiple DPTK-based network stacks, ANS, FStack. But the problem was that the Doka version that we've used was integrated with a newer DPTK version that the network stacks integrated with DPTK were using, which was a hassle to try to bump it up to add additional porting code to just make it work. So we've decided at that stage, considering the amount of time we could spend on it, to just go with lightweight IP, which was significantly easier to work with. And we had some prior experience to working with it, right? So in this case, we have lightweight IP. We've left MQTT processing running on top of it using the socket layer from the lightweight IP. And we left the gRPC notifications from the broker for the subscription topic mapping. As for TCP aspects, obviously, lightweight IP tackled all of them for us. So we're expecting that results are going to be better for a larger load. And that happened. First, we took the scenario that was more complex for the version 1, for TCP monitoring, just to see how the new or the current solution compared to the previous one. And we're seeing that we are even better than even with more code, better than the TCP monitoring, which is kind of surprising, but it happened. We've increased the number of publishers to 60 and subscribers to 5, leaving the rate of the packets the same. Obviously, for the TCP monitoring, that was with 10 publishers, it crashed. With 60, our lightweight IP seemed to fare just fine, and it seems to scale really nicely. What was surprising that the reference solution scaled poorly, but we've just used default configuration without playing around with it, maybe playing around with it.
It was not optimized deployment.
Yeah, right. We just took as is. But we are seeing that we might say that it's complete, right? We've managed to achieve some success, right?
Yeah.
It scales nicely, it works. But we were not kind of 100% satisfied with the overall thing, meaning that, okay, our offload is useful, everything works, but we have additional network stack in between the broker and the client. For MQTT, necessarily, it doesn't have to be a problem, right? Because most of the traffic that's happening between the broker and most of the traffic for MQTT, the publish packet distribution, is happening between the protocol offload and the client. So for MQTT, it doesn't hurt us that much But it would be more pronounced, the introduction of the network stack might impact the latency. It will, between the broker and the client, for all the traffic that's happening there. It might work for more, let's say, balanced traffic that's happening between the broker and the client. You know, the distribution of how much of the traffic is offloaded and how much is handled by, let's say, the slow path between the broker and the client, right? Yeah. And we've asked ourselves, can we get better than that?
And it seems that indeed we could. We came up with a solution we called internally socket interception, and it was actually inspired in some way by the TCP offload engines that I mentioned previously. So in this case, we have focused on removing the connection, TCP connection between broker and protocol offload, and instead we want to somehow expose the network stack we have already embedded in our net protocol offload. So to achieve this goal, we have two main problems. First of all, we need to somehow intercept the calls to socket or provide the socket API. And second problem we will face is the actual forwarding of this data between host and our protocol offload on NVIDIA Bluefield.
Which a sub-problem of the first would be that we don't want to intercept all of the connections, right?
Yeah, yeah. That's the point. We don't, rather, we want to intercept all, but we don't want to forward all the calls exactly. from that the broker does to our backend. So we have created a shim library that intercepts glibc calls to socket. So basically the broker uses glibc interface, then our shim intercepts this call and decides. Sometimes the call is still forwarded to system sockets, which are provided by glibc underneath. For example, that case is present when we want to forward the gRPC data, or other case is that we want to forward calls to netlink subsystem from the broker all the way to the host kernel. But the most interesting traffic is the actual TCP traffic that we want to offload. And in this case, it's forwarded to a new component in our protocol offload. We call it TCP socket backend. And it basically interacts sometimes with network stack directly, or sometimes it pulls for MQTT messages with the MQTT processing. And the important thing here to point out is that the MQTT processing remains nearly the same. This iteration we simply did not concern ourselves. It was not the goal to further accelerate the protocol. We wanted to remove the connection from
we were saying that the traffic between the broker and the client, that's something that we want to tackle here.
Yeah.
So the MQTT processing naturally we expect it not to be worse.
Yeah, and it was not. So with this approach, the result is that the broker uses the lightweight IP network stack nearly directly. There are, of course, a lot of intermediate layers. But the important thing is that we bypass the network stack, the kernel network stack on the host. So it's less overhead in our both in the host operating system and in our protocol offload to actually maintain that previous connection. And since we used the libc shim, we did not modify the source code in the broker in any way. We are still using the broker distributed in system packages. Mm-hmm. So that's an important benefit. So that's all about this iteration. We can move to summary. And a few key takeaways that we wanted you to remember from this webinar is that offloading any user-level protocol, in our example it was MQTT, still requires maintaining all those guarantees from the lower layers. And in our case, TCP offloading is actually the most complex subject.
Yeah, we've also presented that there are many ways that how a user protocol offload can be implemented, right?
Yeah.
You can have it TCP monitoring or do it a more complex way, and how the protocol offload can be integrated with an application, right?
Yeah. And our proof of concept project was still successful in the performance metrics we have chosen. The distribution time of MQTT was reduced at least threefold, and we have arrived with lower CPU load. So it was important for us. So we are moving right now to the Q&A session. If you have any questions, please leave them in the chat, and we will answer them shortly. Meanwhile, you have present a QR code pointing to our ebook. So if you want to, you are very welcome to visit that. And I think we have already some questions.
Yeah, the first one was from Eddie Grunch. I hope that I'm spelling that correctly. The MQTT protocol is running on top of TCP. It's not based on HTTP.
Yeah. However, it's the same. MQTT is the same level as HTTP. So basically, all the guarantees from TCP would be needed for HTTP.
Yeah, if you were offloading HTTP service for some time, yeah. Yeah, sure. So Asaf, Penso, there were a couple of them already. What services do you need from the hardware offload engine? We were mentioning on the hardware pieces slide, we were mentioning that those mechanisms might help the protocol offload, the implementation of it, to provide certain guarantees of the lower layers of the stack for the user protocol offload to implement, or let's say to generate and receive packets, right? For UDP, that would be very simple. We wouldn't even have to probably fight that much with a whole network stack, but that would be something. For the other one, beside the latency results, do you have also packets per second results for each solution? I'm not necessarily, this is the rate of packets that we were sending through. So we were mentioning in the test configuration that we were sending a given packets per second per publisher.
The rate was constant.
Yeah, the rate was constant, yes.
Can you please discuss the security aspect of the protocol and TCP offloading?
Well, that would be a presentation all in itself, but
yeah.
It would depend on whether we first how do we trust it? Do we trust the DPU? Do we trust the smart NIC on the system? Because if it's underlying the host would like to get to,
yeah.
it's all the like the huge discussion of whether the DPU is subservient to the host, or is it like above the host like an IPU device? Or if it's subservient, then you have to establish certain yeah. trust boundaries, right?
I think in this case we can mention as well that the last approach we have presented with the socket interception, that put us in a straightforward way of offloading TLS. Yeah.
Yeah, right. But it would mean that do you have trust from the host side that the network stack is correct, right?
Yeah.
In any way, because on the host side, obviously you have the whole control of the network stack. In that case, you have to trust the DPU to do the traffic management correctly, right?
Yeah. I think we have another message from Asaf, and thank you very much. We will.
Yeah, we'd welcome a meeting, sure.
Yeah.
Do we have any more questions?
I think we can wait like 10 seconds and.
Yeah, sure.
Or not.
I know there is some kind of latency here.
Yeah, so it seems there are no questions.
So I guess we're going to wrap this up. Thank you very much for coming in and listening to us babbling.
Thank you very much. And hope to see you soon.
Yep, take care.